Yeah, as Tanya mentioned, we're going to be talking about two projects today that are very much related and both use satellite imagery to monitor our coastal systems. I am going to be talking about satellite-derived shorelines and how we've used this algorithm called COSAT to extract shorelines over long temporal data sets on our coast. And then Ian is going to take it away on our new START project, which is using those same satellite images and the same COSAT algorithm, but to monitor and detect and track our shoal evolution in our inlet system. So I'll take it away and first introduce COSAT, which is the algorithm that both of these projects really are focused on. So COSAT is a publicly available satellite-derived shoreline algorithm, which is natively written in Python. It downloads publicly available imagery like our Landsat fleet and Sentinel-2. They have a combined revisit rate of 5 to 16 days, and they go all the way back to 1984. So it's a tremendous amount of imagery that we can tap into in our coastal systems. More recently, there's PlanetScope imagery, which COSAT has another branch that it works with as well. So PlanetScope imagery is a little bit higher resolution and a little bit higher resolution in temporal density as well. It has a daily revisit rate and dates back to 2016. And when it downloads these images, it does two things to them. It does a supervised classification, which you see on the top middle panel there, where the dark blue pixels are labeled as water, the light blue pixels are labeled as whitewater, the orange pixels are labeled as sand, and then there's other land features. Additionally, it does a water index on the image, so that is a combination of different image bands. So it's typically a combination of visible bands and shortwave infrared or near infrared bands. And what it really highlights is land versus water. And you can see in the water index image there, the red is showing the land pixels and the water is shown in blue. It then combines those two information sources and it finds the sand and the water pixels and their respective water indexes, and it finds a threshold where it finds the maximum interclass variance between the sand and the water pixels. So it basically finds the sand-water interface on the image, and then it goes and extracts that water line from the images. We then need to do a water level correction since tides and waves influence these instantaneous water lines. So we do a water level correction and we call those satellite-derived shorelines, and we can track shorelines over really long time periods with these image sources. So the first portion of our last project was to create a wrapper around this COSAT toolbox. It's written in Python, so it's pretty clunky and pretty geared towards the research world, but we thought it had really great management applications, and if we could get it into this ArcGIS workflow, then it could really be useful for our district engineer. So we created a wrapper around COSAT so that you could install it and load it into your ArcGIS environment. You then see a toolbox that looks like the middle panel there, where you just need to give it a couple input parameters like a site shapefile, a start and end date, a contour that you want to shift your shorelines to, an estimated beach slope, and a tide gauge number. It then, you hit run and it then calls COSAT up. COSAT then downloads all the images in your area, in your time period, and does some analysis and gives you both raw shorelines that you can use to do your own analysis, but it also generates these plots on the right here, where you can see the colored dots on the middle panel there are showing you for every transect you have across your study site, what is the linear regression for the whole time period of your time period that you looked at. So you can see that in this case in Duck, North Carolina, there was some erosion in the north end of the property and some accretion on the south end of the property. We could also look at each one of those points, which is a transect across your study site, and you can see for each of the images where the shoreline position was for your whole time period. And then they give you a moving average, so you can start to see some seasonal time scales and a linear regression as well. So you could see that at this location on the beach from 2019 to 2022, there was long-term linear accretion, but you could see that there's some seasonal signals that are there as well. So this tool is available on the CIRP website, and you could install it and reach out to me if you have any problems with the install. But that was one of our first deliverables for our satellite-derived shoreline project. But as I mentioned, what gets extracted from these satellite images is an instantaneous water-sand interface. And in order to track shoreline change throughout time, we need to calculate this linear shift from waterline to what we call a satellite-derived shoreline. And that's using the equation on the right there, where delta x is equal to the difference of the elevation of the reference contour and the elevation of the waterline, and we divide that by the beach slope. In practice, we assign the elevation of the waterline as the elevation of the tide at the time of image acquisition, and we use an average beach slope over the whole time span of the study. When we do this linear correction across different sites across the globe, we see that it works really well at some sites like Duck that are microtidal and fairly steep beaches. But when we start to apply it to other sites that have either a larger tidal range or more gentle beach slopes, we start to see these larger STS errors. And these site-specific errors and outputs are likely related to concurrent wave run-up conditions. There have been a number of studies that have looked into adding either additional water level parameters like setup or run up 2%, or by using a time-varying beach slope to start to improve these accuracies. But what's complicated about this linear shift is that there's three variables that are very much related to each other when we talk about this one linear shift and then our STS error. So we have the elevation of the reference contour, the elevation of the waterline, and then we have our beach slope. At Duck, at the Field Research Facility, we have a LiDAR that is pointed offshore. And so for the first time, we have coincident hydrodynamic and topographic data that we can now compare to the waterline that's extracted on the satellite image. And that allows us to ask and answer these three questions. What reference contour introduces the least error? What is the optimal waterline elevation? And how much error does an average slope introduce? And this was really the second part of that first project that I was talking about, really building out an error budget for these satellite-derived shorelines and seeing if we can improve this water level correction at our sites across the United States. So to make things a little bit more complicated, I am using PlanetScope imagery and Sentinel-2 imagery to extract these water lines. The most obvious difference between these image sources is their resolution. So PlanetScope has a 3 to 4 meter ground sampling distance, and Sentinel-2 has a 15-meter ground sampling distance in the visible bands. But they also have different bands that they capture. So we need to use two different water indices when we try to determine what is water and what is land. So for PlanetScope, we use the near-infrared minus blue band combination, and for Sentinel-2, we use the modified normalized difference water index, which is a combination of the shortwave infrared band and the green band. Finally, we use two different thresholding algorithms to extract these water lines. We use the OTSU, which is built into the COSAT tool currently. It maximizes the interclass variance between the sand and the water pixels. And we also use the weighted peaks waterline thresholds, which finds the sand and the water pixel peaks and weights itself towards the sand pixels. So the weighted peaks waterlines are going to be more onshore than the OTSU-derived waterlines. So now we have 4 data sets of waterlines. We have the 2 image sources and the 2 threshold algorithms. Along this green line, that's the LiDAR transect, and you can see the elevation profile for those images on the right there. We can then compare the satellite-derived waterlines directly to the LiDAR-derived waterlines along that green transect. So the first thing we want to show is the cross-shore position of these 4 image data sets and compare them to the LiDAR-derived waterline data set. And that's what I'm showing in these plots here. So for each of our data sets, the image source and threshold combination, we have on the y-axis the satellite-derived waterline position, and the x-axis is the LiDAR-derived waterline position. The Sentinel-2 satellite-derived waterlines, regardless of threshold combination, correlated better with the LiDAR-derived water lines than the PlanetScope satellite-derived water lines. And that's really interesting because the Sentinel-2 imagery is much closer than the PlanetScope imagery. The Otsu-derived water lines, regardless of image source, had reduced error when compared to the weighted peak satellite-derived water lines. And then finally, the weighted peak satellite-derived water lines had strong onshore bias compared to the LiDAR-derived water lines. But when we go back to this question of what is the optimal waterline elevation to assign these satellite-derived water lines, we'll never have these LiDARs along our beach sites that we could use to correct these satellite-derived water lines. So we wanted to start thinking in terms of bulk statistics as well. So we calculated the cross-shore position from that measured LiDAR line scan, the run-up exceedance from 2% all the way down to run-up 98%. So really to get at what run-up exceedance correlates best with the satellite-derived water lines. Are they usually in the mean swash? Are they in the upper extent of the swash zone? So we calculated the cross-shore position of each of those exceedances at the time of image acquisition. And we did a direct comparison with the satellite-derived waterline position and the run-up exceedance position. So on the x-axis here is that difference of satellite-derived waterline position and run-up exceedance position. For each of those run-up exceedances, you have our 2% in blue all the way to our 98% in more of an orange-purple color. And this is for the Sentinel-2 Otsu dataset. In the top right hand of that plot, I showed you the lowest RMSD run-up exceedance for this dataset. So for Sentinel-2 Otsu, run-up 80% correlated best with those satellite-derived waterline positions. You could see that this differed for each of the image source and threshold combinations, and it ranged from 20% to the mean swash. But you could also see that the Otsu-derived waterlines, regardless of the image source, correlated more with the mid-swash, while the weighted peaks waterlines correlated more with the upper extent of the swash zone. So we also wanted to calculate parameterized run-up exceedances since we don't have these measured bulk statistics anywhere else. So we calculated our parameterized run-up exceedance elevations using the Pomston and Holman variation of the Stockton equation presented in 2012. And you can use this equation to calculate, again, a range of run-up exceedances by calculating this different eta sub sigma for a range of about 2% through 98%. We have a wave buoy, so we have the offshore wave height and wavelength. So we got these run-up elevations for each of our image source times, and we have our parameterized run-up exceedances. We could then intersect that with the LiDAR line scan at the time of image acquisition and find, again, the cross-shore position of our parameterized run-up exceedances for our 2% through our 98%. We found the lowest RMSD run-up exceedance using the parameterized as well. And now I'm showing you the cross-shore position difference between the bulk position and the satellite-derived waterline position. So you could see the black is the tide cross-shore position, and you see in all four of the data sets, there's a really strong onshore bias for the satellite-derived waterline position. So we know that we could do better than tide. With our measured and our parameterized run-up exceedances, our measured is shown in the colored lines and our parameterized is shown in the gray lines. You could see that both of those bulk positions line up better with our satellite-derived waterline cross-shore position over tide. And you can see that we are improving this satellite-derived waterline assignment for these parameterized run-up exceedances. Okay, so now we're going to move on to our second question of how much error does an average slope introduce? And in order to do that, we calculated the measured slope at the time of image acquisition between the elevation of the reference contour, which for our study we assigned as the 1 meter elevation contour, and the cross-shore position of the satellite-derived waterline. So we found that exact beach slope in that portion of beach at the time of image acquisition. And that's what I'm showing for each of the data sets, a histogram on the right there. The black line is showing you the average beach slope for duck, which is 0.08. And you can see that in all four of the data sets, the measured slope has a wide variation that's not captured using the average beach slope of 0.08. Now, next we're going to jump over to this third question. What reference contour introduces the least error when we convert our satellite-derived waterlines to shorelines? And to do that, I'm going to show the cross-roll position of 3 things for each of the 4 data sets. I'm going to show the cross-roll position of the 1 meter contour, which again is the reference contour for our data set, the satellite-derived waterline position, which is shown in the colored line there, which is blue, and then the parameterized waterline position, which is shown in gray. You can see that the satellite-derived waterline position and the parameterized waterline position align really well across the whole data set. And they actually align really well for all 4 of our data sets. So again, the 1 meter contour is shown in black, the satellite-derived waterline position is shown in each of the colored lines, and the parameterized waterline position is shown in the gray line. I also included the mean elevation for each of those data sets in the bottom of each of the plots. And what's really interesting is that the PlanetScope Otsu data set is much further offshore and in lower elevation than the remainder of the data set. So the mean elevation of the PlanetScope Otsu data set is 17 centimeters. And again, we are shifting the satellite-derived shorelines to the reference contour of 1 meter. So when we think back to this equation, delta x equals the difference of the elevation of the reference contour and the waterline divided by beach slope. And if we take the 2 PlanetScope data sets, so Otsu and weighted peaks, and we fill in this equation with our average beach slope and mean elevation, you could see that the numerator of the PlanetScope Otsu data set is larger, and we know that 0.08 is not always representative of our beach at the time of image acquisition. So by having a larger numerator, we are trying to shift the water lines further, and we're allowing that slope error to really propagate into our SDS error. So when answering this question of what reference contour should we shift our satellite-derived waterlines to, we've concluded that Otsu satellite-derived waterlines are lower on the beach and should be shifted to the mid-swash, whereas weighted peak satellite-derived waterlines are consistently in the upper swash and should be shifted to an elevation within that zone. So now we're going to shift our satellite-derived waterlines to shorelines, and we're going to do that using a variety of ways to fill in these variables. We're going to assign the waterline elevation as tide, the lowest RMSD measured bulk statistic, and the lowest RMSD parameterized bulk statistic. We also can use an average beach slope and a measured beach slope, but we're all going to shift them all to the 1 meter contour. So I'll walk through those satellite-derived shoreline errors now. First, we're going to assign the elevation of tide and use an average beach slope. And you can see the cross-roll position of the converted SDS is on the y-axis, and the cross-roll position of the measured 1 meter contour is shown on the x-axis. You see that we have RMSDs for Sentinel-2 satellite-derived shorelines ranging from 9 to 10.5 meters. And for PlanetScope satellite-derived shorelines, they range from 7.5 to about 10 meters. And these errors are pretty consistent with previous literature. Now we can convert our satellite-derived waterlines to shorelines using the lowest RMSD measured bulk statistic and our measured beach slope. And you see that our satellite-derived shoreline RMSDs reduce considerably. Our Sentinel-2 satellite-derived shoreline RMSD reduced by 30%, and our PlanetScope weighted peaks RMSD reduced by about 40%. And you see that our Sentinel-2 satellite-derived shorelines now have a range of RMSD from 5 to 6.5 meters, and our PlanetScope satellite-derived shorelines range from 5 to 6 meters. Now using the lowest RMSD parameterized bulk statistic and a measured average, and an average beach slope, this would be what we could do in practice at other sites across the United States. You see that we still have a reduction in RMSD considering just tide and average beach slope. So now our Sentinel-2 satellite-derived shorelines get as good as about 6.7 meters of RMSD, and our PlanetScope satellite-derived shorelines have an RMSD of about 7.9 meters. So I'm just going to wrap up this portion of the project, and the main takeaways from the satellite-derived shoreline work unit was that we extracted water lines using COSAT from 2 image sources and 2 thresholding algorithms. We really were trying to build out an error an error budget for the satellite-derived shorelines, and we found that the Atsu waterlines correlated better with both the LiDAR-derived waterlines and the mean swash statistics, whereas the weighted peaks waterlines correlated with the bulk statistics in the upper extent of the swash zone. By using the measured run-up bulk statistic and measured beach slope, when converting to SDS RMSD was reduced drastically for this data set, but it also was reduced when we used parameterized run-up bulk statistics and average beach slopes, and that has some potential to use at less studied beach sites. We also wanted to take this back to the tool and give you some management application with this study. So using our satellite shoreline mapper, we use the Atsu threshold algorithm on Sentinel-2 and Landsat imagery. So in using the current tool, we really suggest you shift your satellite-derived waterlines to a contour that's consistently in the mean swash, and that's going to be filling in that contour input parameter that is part of the toolbox currently. And hopefully we have a future version of Satellite Shoreline Mapper to include additional water level corrections above tide may be set up to reflect these findings. So that's all for our satellite-derived shoreline work unit, and I'm going to pass it over to Ian, who's going to talk about our inlet shoaling.
Thanks, Shannon. Appreciate you wrapping up that last portion of our shoreline work. And I'll just add that's Shannon wrote up a great manuscript that's under review, coastal engineering, so stay tuned for that. And as you can all see, this is very detailed work. I think there's, we could try forever to improve the accuracies, but I think we're excited also to explore the applications of satellite imagery beyond just shoreline, open coast shorelines themselves. So we're going to switch gears here a little bit, and as Tanya mentioned, talk about this new start within CIRP. And so I'll just begin here by showing you Manasquan Inlet, New Jersey. This made the press several times over the past year just due to shoaling issues. And if Shannon advances one for me, you can see this very impressive shoal feature within the inlet throat itself, and it represents about 1/3 of the inlet width, which of course is a challenge to navigation. Next slide, please. I know this caused a lot of issues, and they had to sort of rapidly mobilize to dredge this channel. And you can see here the surfer's having some fun on that shoal feature, but there's multi-use conflict here with navigation in a busy waterway here. So shoaling again is a significant challenge, and a couple of statements of needs were submitted recently in the past year or two. Initially from Monica out of Philadelphia and Rachel out of Detroit. And so I guess the synthesis from those statements of needs were that we need sort of better predictive tools, better monitoring capability, better remote sensing approaches to first detect and then hopefully track these shoals along our coastlines. Next, please. And so as you heard from Shannon, CoastSat is a pretty powerful tool used primarily for sandy coastline shoreline extraction. It's great. As she mentioned, a tremendous amount of data dating back to 1984. And so as we're shifting gears here, we really started to think about, can we use this whitewater classification that's inherent to CoastSat to start to identify wave breaking over shoal features within inlets. And so the whitewater currently is used to sort of improve the accuracy along the open coast to eliminate your wave breaking zone. But again, we thought that this could be a critical piece as we start to identify shoal features within inlets. Next. And so we did just start this new work unit in the fall, but we're excited to show some preliminary data from a few case studies across the country. And so again, we'll be focusing on wave-dominated inlets, and you can see a couple examples from our tool here, both in North Carolina at the top, New River Inlet. This is notorious for high wave energy and shoaling. And you can see on that panel to the right how nicely COSAT classifies those whitewater pixels where waves are breaking over those shoal features on the ocean side. And then a little farther south, to the north, tucked back somewhat in the Chesapeake Bay, we have Lynnhaven Inlet. And on this day in particular, you can see waves also breaking over that shoal, those shoals sort of on the open side. But if we advance the slide, we can see that, one more please, within that sort of protected Chesapeake Bay, we don't always have high wave action. And so this other example down in the bottom there is showing a small or no wave day, so we have no signature of those shoal features or waves breaking over them along the open coastline there. So if we start to think about our tool, and then sort of another work unit, as Tanya mentioned, we're working sort of closely alongside with Justin and Alex on a similar work unit. They're taking a somewhat different approach, and so they'll be sort of more geared toward lower wave energy environments. And so if we think about sort of our approach, we can use it in wave dominated areas, but when we have, we might sort of identify a wave threshold. So once waves are lower than what we define, or we're in an area with just low wave climate, we might start to use more multispectral and optical approaches, as shown here from the example from Justin and Alex. And so they're using additional classes, and so I think the goal eventually here would be to sort of couple both of our approaches, depending where you're at in the country or world, and sort of use this combined sort of approach. Next slide. So moving through just a couple of the examples here. I don't think Kelly from Jacksonville's on today, but we've started to get some input from the field, and certainly welcome to more inlet areas that might be challenging to manage in terms of shoal development and migration. Kelly had suggested we check out this Matanzas Pass outside of Fort Myers in Florida. And you can see here on the top plot in October of 2020, we had you can see some boat traffic. You can see maybe some sort of shoal start to develop here on the sort of northwest portion of that island there. But then a few months later, you can see this shoal is much more well defined. It's welded to the island itself. Potentially some waves are starting to break over it, and you can see that really nice white feature that is starting to impact the waterway. The resolution's a little hard on my screen, but anyway, this is an approach that you could start to track that sort of development and then migration into that waterway, where a lot of boat traffic sort of hugs the island and goes east under that pass and that bridge there. Next slide, please. You can also think of this as not just tracking shoals within inlets, but also as sort of a first pass or sort of investigatory tool to look at the formation of inlets themselves and sort of the recovery and closure period following a storm. So as you know, there was a very active storm season, and again in Florida. And so this past fall, Hurricane Milton struck on the Gulf side, and we did a little bit of post-storm response work, looking at sort of the impacts and recovery along that Florida coastline. And interestingly, you can see here from northern Captiva Island in Florida, the tool identified actually some new breaches along this slender portion of Barrier Islands following the storm event. And What you can also note is in the bottom panel, you can see the shoreline is pretty well traced in the black lines. And so what you could do is actually, track and quantify that closing period following the storm. And you could see that this island potentially weld back together. And so this, again, is sort of a nice first pass sort of reconnaissance-based tool as well. Next slide. So here's just a time series of, I think, yeah, five years of imagery from Manasquan Inlet that we started with on my first slide. And so again, note the variable white colors along that open coast side on that right panel, and you can see again the shore break or waves breaking along the coastline, but you can also see times when they're breaking over the shoals, both in the inlet itself and also outside of it, which both present navigation hazards. And also you can see that bump within the throat itself, as I showed, that represents about a third of that inlet width in the beginning of my portion of the presentation. Next slide, please. So here's another sort of longer look at Barnegat Inlet, New Jersey. This one's sped up a little bit. This is about 4 years worth of data in Barnegat based on input from the field and the management challenges there. We've selected as sort of our initial pilot site for our efforts this year to spin up our sort of workflow and data pipelines. Again, you can see variable whitewater classification throughout this domain as well. Next slide. So this is hot off the press here, but what we can start to do is do more temporal analysis. Again, this data dates back, it's free public data, dates back to 1984. And so this is just using the 4-year data set of imagery, and this is essentially a composite image of the brightest pixels, and I've used that yellow arrow there to highlight where we have some frequent shoal development, where again that pixel is brightest throughout that 4-year period. And you can ignore some of those nasty white areas just from the cloud masking. This is again sort of in development, but this is sort of one of our first passes at sort of investigation and how we can start to quantify some of these processes into a tool output. Next, please. So I mentioned, we've talked plenty about COSAT today. Again, that is free, publicly available satellite imagery. It's somewhat coarse in resolution, but the algorithms operate on a sub-pixel basis. But that we also have some other imagery available through Planet Scope. That's 3 to 4 meters pixel resolution. You can see some dollar signs there. In the past, we've had to purchase that imagery. It is pretty promising. We've learned that I think we can potentially access this also for free through a NGA contract. So that's sort of in the works right now as well. That could be another powerful data source, higher resolution to districts as well. So we'll be looking at both of those imagery products and the COSAT classifier. But if Shannon advances here, we're also going to investigate this new classifier called Coast Train, which splits it out into many more classes. And so we're going to see, just first off, does this classification do any better than COSAT itself on the same imagery? And then also, can we use this to inform sort of our wave threshold, where we have maybe lower wave heights? We can actually look into the subaqueous sort of side and maybe better identify these shoals using this Coast Train machine learning approach. So in total, we'll be looking at 4 different data pipelines: normal COSAT Planet Scope, and then Coast Train on each of those to try to identify what's the best sort of accuracy and what might be best for different applications. Next, please. So in terms of potential products, we've held our PDT kickoff meeting. We got some great input so far. Still sort of open to any more ideas from the field or from any ERDIC folks. But if you think back to our shoreline tool there to the left, we'll be planning to add additional functionality for inlets, and some examples are shown here. So first off, we can still leverage that shoreline extraction and sort of identify changes in the inlet geometry, not just on the open coast, but we'll be testing it on sort of the back barrier and on the inlet limbs. That will be pushing the algorithm a little bit beyond just the sandy sort of substrate, and see if it can handle sort of the marshy areas as well. But you can think of having a time series of your inlet configuration over decades. And then you can see that heat map there. If you think of those being shoals, you can just throughout your inlet or your study domain, identify areas that have the highest probability of shoal formation in the past. And you could start to use that to sort of inform, future surveys or to mobilize a dredge. So again, sort of maybe an initial pass at helping with operations. And then lastly, you can see some of these hypothetical shoal directional vectors. So once we identify the nodes or the centroids of those shoals, we can start to look at which way they're migrating and how fast. Next slide. So just really quick to summarize, we have 4 years planned of work. Again, this first year is really focused on spinning up our workflow at a single test site. We'll sprinkle in, I'm sure, some case studies as I've showed, but we're looking at a 10-year period. And then next year, we're planning to ramp up the sites, summarize in a technical note, and then really focus on tech transfer in the third year. And then if things are going well, attempt to create some very core sort of shoal predictive model based on environmental forcings, wave, wind, etc., and then summarize that all in some sort of publication. And so I think with that, we wrapped up. I know that was pretty lengthy, a lot of material, but happy to answer any questions both about the new start and then Shannon's shoreline work. Thank you.